today we are getting started with a QSL Spotlight. So QSL, the Quantum Solutions Launchpad, we have been running this program for an year now, and I wanted all the participants of the QSL program, all the QSL fellows we have had to come and share their experiences, their projects they have worked on today, so that you can get an idea of what kind of projects are built in the QSL program at Womanium, and also ask any questions you might have from the QSL fellows themselves. The first session is with Mandy Bowman. Yeah, so while Mandy tries to share her screen, a quick introduction of the project. The team spent about six and a half months on trying to build quantum variational algorithms with tensor networks and sets to solve the Poisson's equation. And they did it pretty good. The team was invited at NATL to present their project to the leadership over there. The team was also invited to present their project as a poster at the PQI Quantum Conference. And the project also won about $150,000 in quantum hardware grants from INQ and QMG collaboration. So that is a huge deal.
So I graduated with my master's last year, and I did research in quantum algorithms to solve for nuclear spectra. And then I participated in the Womanium Quantum Workshop last summer, which led to joining this Quantum Solutions Launchpad Fellowship, where I was able to start a project with the Naval Nuclear Lab. And so for our project, we had a pretty open-ended objective. Essentially, they told us to find quantum algorithms that had analogous engineering problems that you'd come across. And we had the option to either deep dive into a specific problem or do more of like a surface level evaluation. So through our literature review, we came across some papers on the Poisson equation. And so we decided to just kind of go with one paper that we thought was interesting. And it had a more recent publication focused more on NISQ-friendly algorithms, and it had an available code base that we could work with. So we decided ultimately to focus in on this one algorithm. And so in this algorithm is by Sato et al. They use a variational quantum algorithm, which I can do a brief overview. So if you're familiar with the VQE, with the variational quantum eigensolver, that's a pretty common VQA. So essentially you start with an ansatz, a guess to the solution. You encode and prepare your states on the quantum computer, and then you measure some expectation values. And then you optimize these parameters, and then with a new set of values, you run this loop until you reach some threshold or convergence. So in Sato et al., what they did was they essentially replaced this cost function where that would be in the VQE with this cost function, which they derived by minimizing the total potential energy of a system. And they recognized by minimizing this equation, we can actually recover the Poisson equation. And so, as I stated, one of the important factors in the VQA is your choice of ansatz. And so in Sato et al., they used a hardware efficient ansatz. They didn't do a very deep investigation into different types of ansatz. Hardware efficient ansatz is a good starting place because, as it says, it's efficient for implementing on like NISQ devices. However, it doesn't necessarily mean that it's going to be a good form of a solution for this type of problem. So we wanted to look into using tensor networks as our ansatz, which we can play with the connectivity and entanglement of this problem. And so I guess I should say, so two of the common architectures for tensor networks are the matrix product states and the tree tensor networks. So we looked into both of those. And as you can see on the bottom here, this is kind of how it translates into a quantum circuit. And so for a more specific example, on Qiskit, this is what it looks like. So you have some rotation gates, some control gates, and different variations of entanglement. We played with using different types of rotation gates, different types of control gates, using more parameters, less parameters. And so these are the results we ended up with, trying about 4 methods. And so what we saw is the matrix product state actually gave us the best results. The tree tensor network did not perform as well. And so we ran these for 3 different boundary conditions. And we found that for periodic, we got about a similar solution quality as the hardware efficient. However, we got an improvement in the Newman boundary conditions for the solution quality, as well as the variation in the solution, as well as a bit in the Dirichlet boundary conditions. So one of the main contributions of the Sato et al. Paper was that not only the solution, but they could also find the norm of the solution. And so we computed these also, and again, in the Newman boundary conditions, our MPS ansatz did a better job of finding the solution compared to the classical solution. And then looking at the cost of running these, here on the left, we have the number of circuits that had to be run. And for the Newman and Dirichlet boundary conditions, we were able to find the solution in fewer, by running fewer circuits, as well as in fewer iterations. The periodic boundary conditions were pretty similar. And so based on this, we were concluded that the MPS-based ansatz led to better solution quality, lower variation, and required fewer iterations and circuit runs. So this was a viable method that was also efficient, but had a better form of the solution for this problem. So this was what we completed in the first phase, which is what we presented at NETL. Since then, we have worked on addressing other limitations of this algorithm, such as addressing like the gate depth, barren plateaus, and such. And so Geeta has joined us today, and she actually joined in the second phase. And she worked on reducing the gate depth a lot. So I don't know if you want to discuss that a little bit, Geeta, and maybe you can talk about your experience also. I think you're muted. Oh, it unmuted and then remuted. Okay, there we go.
Thank you, Mandy. Great introduction. I'm Geeta, doing my PhD in computer science, and I was being an intern of QSL from this January. I had a great opportunity working with the innovative projects. The project we were working on this quantum mini apps for engineering applications, where we apply the variational quantum algorithm. As Mandy discussed, on the first phase, they were come up with the debate and explore different type of answers, how it works with our problems on minimizing the potential energy. My experience is that, so how to reduce the depth and stuff. So for that, I will do, instead of using the sparse Pauli operator to reduce some gate reduction, and also we use some of the recent optimization technique which is available in Qiskit. From that, we will get a better result, and still we are working on how to implement in the real hardware.
Yeah, thank you once again, Mandy and Geeta. Next up, we have Ron and Anjali, who did another very interesting project, and this was more focused on real quantum hardware. So Anjali and Ron were working on building a quantum sensing hardware design, and they were pretty successful in building that.
All right, thank you. Yeah, so my name is Ron Schreiner, and my research partner, Anjali Twazan, researched some quantum sensor technology based on nitrogen vacancy in diamond crystal. I won't get into too much of the specifics of the quantum technology. Basically, diamonds are made of carbon in a very tight lattice, and every once in a while, a nitrogen atom gets injected, and it creates a vacancy. That vacancy somewhat acts like a qubit, and it's exploitable. So, a little bit about me. I was a graduate of the Womanium summer school last year, and was asked to be assigned to a project like this through their fellowship. And this has been really quite fascinating, and it relies on a lot of experience I've had in the past. It's basically quantum and hardware at the same time. So this was sponsored again by the Naval Nuclear Laboratory, and was a QSL project with Womanium. The project overview: this was to design a low-cost handheld quantum sensing device based on the diamond nitrogen vacancy centers. The final design will serve as an educational tool for teaching of quantum hardware technologies. Some of the specific requirements is we needed to be able to measure ODMR spectrum to derive magnetic field or temperature measurements. We had a target price of $1,000 or less, and that was a bit of a challenge. And the final design could not require, an academic lab full of optomechanical or rack-mounted expensive infrastructure. It had to be small and lightweight enough to be carried by hand, and it should be understandable to a wide range of audience participants. We also had, there was also pressure to use commodity parts, off-the-shelf parts and tools and other resources available to schools and hobbyists. And there was a preference to use US-based companies for ordering parts and services. Some of our key results were we created a project vocabulary document. Entering into a project like this, the first step was to do a lot of research. So it was very good to just start compiling like a dictionary. We also reviewed a number of papers that showed how this was implemented in laboratory areas. So we completed a list of these different these material spreadsheets that showed how each one of these implementations were made, and we had a master inventory sheet so we could keep track of what parts were used. We also had a comparative spreadsheet or a matrix that allowed us to quickly compare one design to another. We used engineering decision trees to make some decisions, and in the end we wound up with 2 conceptual designs. Here's one of the decision trees. In this business of using a diamond as a sensor, you're basically looking at a synthetic diamond, and there's many different ways to grow the diamond and to get it to do specific things. So based on our cost constraint, we pretty much had to settle for one of the most entry-level diamonds created through chemical vapor deposition. There's also, not only can you choose a diamond, you can choose different ways in which it is implemented, whether you have surfaces like reflective surfaces attached to it or not. Here's another decision tree. This was to understand how we would implement the command and control of the device, whether it would be completely self-contained or whether it would be connected to like a laptop, or even maybe sometime in the future could be connected to a smartphone. So you can see on the left here, there was a pretty simple choice of choosing a PC via USB connector. And on the right, you can see what all the things that would have to go on if the device was self-contained. So a lot of some of the things we had to learn and did learn was, how does ODMR work? There's a broad range of implementations and performance. Many of the designs use microwaves, so we had to be able to look at Smith charts for calculating the impedance of microwave antenna elements. There were several options for visible light source pulses and microwave pulses, and the measurement timing window timing. So depending on how you sequence these events, the light pulses, the microwave pulses, and the timing window, you could get the vacancy to operate in slightly different modes. We discovered there was an analogy to the DiVincenzo criteria for quantum computation, which he developed in around 2000, and it basically defined a set of 4 necessary attributes for a quantum system to function as a sensor. This is one of the designs that we came up with. This is a fairly self-contained. You can imagine this is about the size of a D-cell flashlight. What's going on here is we have a compartment where the control and electronics would live. In this particular rendering, we have a green LED as the green light source. We're funneling the light through a conduit here, like a light pipe. The final design, we eliminated the light pipe and moved the LED right down to the crystal element itself. So basically what happens is you irradiate the diamond with green light. You adjust by using microwave pulses, you can adjust the center frequency of the radiation. This has an effect of changing the energy state of those vacancies. And then what happens is, as magnetic fields pass through the diamond, it'll cause those vacancies to decay at specific rates, and that's something that you can measure. Also in this design, we show that there's a lens here that's right down on top of the diamond. This was also eliminated, and basically will be replaced by a CCD camera. The top part here would be the electronics for the imaging, and that would be funneled back through one of the controller boards to go back to the host PC. Let's see. So here's a block diagram of the design. Again, you have a host PC, a USB connected connection to an Arduino. There was a second Arduino Nano. These are identical microcontrollers. Decided to use a separate one to control the timing of the LED pulse and the microwave circuitry, just so we wouldn't have any issues with bandwidth. The top Arduino is used for communications and for bringing the imaging from the CCD sensor back to the laptop, or again, it could eventually in the future be a smartphone. So on this devices on the laptop, you would control and read back the information for an analysis. But again, you can see here, green light irradiates the diamond. Microwave antenna loop can adjust the center frequency of the radiation. And again, this requires some fairly precise timing to make this happen so that we could get a result. This particular design actually came in parts. Once we eliminated a few of the other parts, like the lens and the light pipe, came down to around $600. And I'm going to ask Anjali to step in here and talk about this second design. Anjali?
Thank you, Ron. So for the pen design splits into two different modules. We have the control module that houses the Arduino and the microwave synthesizer, as well as the laser diode, the beam splitter, and the photodiode. And then that control module is connected to the sensor module or the pen module via the coaxial cable and the multi-mode optical fiber. And Ron, can you go back?
Sorry.
Thank you. And so in the sensor module, the diamond sits on top of a quarter wave resonator, which is made up of a quarter wave transformer and a quarter wave open stub. And that is created using copper wire. Next slide, please. And so with the pen design, we realized that there's opportunities for exchangeable tips, whether it's to change out the diamond for like different characteristics. And so these are some of the ideas that we came up with, but we are so far leaning towards the design on the right with twisting the cap and the back completely closed, protecting the circuit that holds the diamond so that we are not always reassembling the circuit every time we take the cap off.
So this is a summary. This was the presentation we also made to the National Energy Technology Lab in Pittsburgh a little while ago. And we'd like to give special thanks to the Womanium team and to the people at NNL and actually for NETL for hosting this presentation at their facility. So without any further ado, I guess we're open for questions.
Wonderful. Thanks a lot, Ron and Anjali, for an amazing presentation. I think you sparked quite interest in the Discord chats. A lot of people are interested. How were you able to bring down the cost of building a big quantum sensor under $1,000? That is a huge achievement. And just to add on to that, this particular project was also invited at one of the largest energy labs in the States, NETL, to present their project to the leadership over there. They were also invited to visit some of the state-of-the-art quantum sensing labs to learn from what is happening in the biggest energy labs in the US. So yeah, this QSL program opened up a lot of opportunities for the fellows. And I think this is kind of an encouragement for all the new participants over here to keep grinding, keep doing all the assignments and quizzes, completing all the modules, performing really well in the projects. So you can also be one of the QSL fellows in the months to come, so that you can also build some really amazing projects and showcase your work to the industry, to the academic field, and really propel your career in the quantum system. Quickly fielding some questions from Discord. Just one question in the interest of time. While you were bringing down the cost and the size of the quantum sensors, did you also realize a dip in the efficiency or the working of the quantum sensors?
So if you'll remember, the purpose of this project was to build a device for educational purposes. So there wasn't a heavy emphasis on performance. Many of the papers that we researched claimed performances in the range of being able to sense magnetic fields at the picotesla level. That's ridiculously small. Some of the papers even theorized that with high-end precision instruments, you could even go smaller than pico, or was it exotesla? It's very, very minute. when you're looking at sensitivity in those ranges, you have to have really high-end precision equipment. So again, we were tasked at creating an educational device. We basically needed to make a device that would demonstrate the phenomena of being able to radiate a diamond crystal, pass a magnetic field through it, and then be able to read back results that showed that the magnetic field passed through it. So it's just a matter of how we reduced cost. Was we avoided expensive optics, we avoided lasers, we avoided specially polished mirrors or filters, and the biggest challenge was getting the microwave circuitry down to a size that would fit within our container or our enclosure. So there were definitely challenges. We definitely are giving up precision, but once again, this was to just demonstrate the phenomena, and we believe there will be no problem with doing that.
Right. And I think this also brings up another point. If there are people in the audience today who are interested in maybe bringing such kind of a hardware to their own industries, maybe low-cost quantum sensors they want to already start working in, or maybe exploring quantum sensors in their current portfolios, I think this is a very good opportunity to connect with the team over here and see how we all can work together and, yeah, explore quantum sensing devices for the industry. Okay, so now I think this is time for the third and the last presentation for our QSL project for today. And I would like to invite Erica to talk about her project. Okay, so over to you, Erica. Could you give a quick introduction about yourself, your project, and then get started?
Yeah, some of you who may have seen me before, I am back, whether you like it or not. I participated in the Womanium 2023 program last year, and upon completing the assignments and doing well on them, Womanium was kind enough to invite me to join them for this Quantum Solutions Launchpad adventure. So it's nice to be back, and I'm gonna give a brief talk about the work I did. I also gave this talk at the National Energy Technology Lab back in April. So this is another one of the things that, like, as part of QSL, they sponsored us to go to this trip. So join QSL, do cool things. And with that, I'm going to share my screen as soon as I find the button. Here we go. All right. Is it behaving?
Yes.
Great, excellent. Oh, got a pop-up screen here, go away. All right, so today I'm going to be talking also about the Nitrogen Vacancy Center, but this time from the theoretical side, that is software. So without further ado, this is the Nitrogen Vacancy Center. This is a blown up image of it. So what we have here is the carbon atoms, which are in dark gray. They are oriented in the rhombohedral configuration, and that creates the diamond lattice. This is the natural configuration for diamonds. Now there's something called a point defect, and that is, in our case, a nitrogen. It doesn't have to be nitrogen, but that is the case that we're going to discuss today. And that's here in blue. Immediately adjacent to it, there is a missing carbon atom. This is the vacancy, and that's that little kind of greenish circle there. That's just empty. However, you will note that the black things, which are the electronic bonds, those are still oriented towards the vacancy, and that's important because they kind of participate in the overall system's physics. So these things here are still oriented towards where the carbon atom used to be. The very last part to setting up the system is that the surrounding lattice donates an extra electron to this system, and it is this electron bobbing around in there. It has it has a quantum spin, as does the nucleus of the defect, and the coupling of the quantum spins of this electron with the nitrogen's nuclear spin. This is what makes this system a qubit. That could be used for computation or sensing, but here we're going to use it for sensing. How? So what I just showed you is the physical picture, but when you start thinking about like all that stuff that you probably learned in like a high school or first year college chemistry class, you learned about like things called electronic shells, right? When you start doing quantum mechanics, you start seeing it like this instead. It's not just discrete shells of SPDF. You can start getting more complicated descriptions that are more accurate. So this is a description of that. So we have three main states here in blue. So that's the 3A2, 3E, and the 1A1 here, here, and here. These are the three main states. However, due to the nature of the coupling of the spins and other interactions with the surrounding environment, you can start splitting them out. So these two are triplets, which is to say that they split into three separate levels here, and that's an orange. However, this one over here is a singlet, and it doesn't split. It just hangs out because it's a singlet. So you got your triplets, each with three, and your singlet with one. However, we're not done yet, because it turns out that with additional coupling, you get part two, which is hyperfine coupling. So not only do the electronic interactions contribute to the splitting, also there are these things called hyperfine and nuclear quadrupole. So to put this all in context, the orange lines are due to electron-electron interactions. That always exists because all systems always have multiple electrons. However, the nuclear quadrupole may or may not exist. It depends on the nucleus of the point defect. So only some of them, only some species will have this. The hyperfine interaction is one of the deep mysteries of physics, and we're not going to discuss its origin too much, but these two things also create this splitting here, and that's shown in green. So you have, here we're just showing the ground state. This would also exist in the excited state of the 3E triplet, and there would be a version of this hyperfine splitting, like these green levels, that would also exist for the singlet state. I just didn't show them here because that would make the slide too complex. So we have regular structure, fine structure, and hyperfine structure. And depending on what you are trying to sense, what you are using your quantum sensor for, different parts of this will become important. After all, if you don't need hyperfine interactions to properly describe your system, don't include them in your math, because it's just computational expense to compute something that is ultimately useless to your scientific pursuit. So how do we actually do this mathematically? After all, I can't take an electronic diagram and stuff it into a computer. That doesn't work. Instead, we map this to a Hamiltonian. So assuming it is perfectly isolated and that nothing is interacting with it, we have this Hamiltonian. So some of the letters you saw in the previous slide, these D, Q, A, these things that are energetic constants that explain the splitting, that's represented here in the Hamiltonian. So again, we have this D, Q, and A. And if the system were perfectly isolated, this is how it would evolve in time. That is to say, if I started time t = 0, and I let it go a couple of seconds, or really milliseconds, how much would it change? This equation tells us this. Now, this is a unitary equation, which is to say it's reversible. Okay, remember, that's an important quality for quantum computing and quantum sensing. However, not everything is reversible, because if you have something that is interfering with the system, like an external magnetic field or an external electric field, or you're pushing on the diamond, like straining it somehow, then this equation will not work, because you're going to have things that are non-reversible, like decay. Okay, and those are irreversible dynamics. So we need a better way to explain this, because if the Hamiltonian describes the reversible symmetry, you need a way to do it the other way, non-reversible. And that's done with the Lindblad quantum master equation, which instead of solving for the Schrödinger equation psi, here we solve for the density matrix rho. Okay. And so we take this Hamiltonian, we put it here, and we do this huge equation. For those of you that are familiar with this, the L operators, these Lindblad operators, those are just projections from final to initial, initial to final states. That's all they are. Okay, so what are we trying to do? There are a lot of papers out here that try to simulate this system for various purposes, whether it's one little piece or a larger kind of overview. There are a lot of papers out there that simulate this. However, because they only focus on specifics, there's no big kind of overarching idea here. right? There's no software that does it all. So the idea that we had was to develop a user-friendly application that simulates the dynamics of the color center using under different conditions, whether they are magnetic, electric field, strain, whatever, right? And the question was, what if we had different point defects? For example, what if it was a different species other than nitrogen? You could have certain isotopes of carbon, okay? That is also allowed. So what if you had a system where you could just plug and play different components? That's what we're after. And to do this, we are going to use a Jupyter notebook with the Python module Qtip, because it's open source, it's easy to use. And the idea would be then we could like write a user manual, and then somebody could could plug and play, even if they're not comfortable with software development. Because some people just want to put in a number and get an answer. And that's what we were hoping to do. We ran a little bit out of time to do this because the background research kind of coming together to do this took a little longer than anticipated. So this is the goal, and we're hoping to continue this work if given the opportunity. But this is where we are today, and we're all ready to go. It's just a question of actually sitting down and doing the software development. Yes, and with that, I would like to thank everybody who contributed to this project, both the Womanium staff who enabled this opportunity, as well as the Naval Nuclear Laboratory, particularly Brian McDermott and Jesse Holmes. And I also want to thank the people over at the Idaho National Laboratory, because they actually gave us compute resources on their HPC infrastructure. And for that, we want to thank Mr. Daniel Kelly at NNL for facilitating that access. So thank you, everyone.
Wonderful. Thanks a lot, Erica. It was great to have you again today and talk about the
Happy to be
project.
back.
And to all of us, so you've had some very interesting partners over the years. I will quickly share my screen to give a quick shout out to all of our partners. And yeah, over here you can see some amazing partners who have been supporting the entire Womanium program for the past few years. This list has grown even beyond these 50 listed over here. Specifically regarding the project, Xanadu, from Ultra Space, CQ Tech, Qubit, they have all hosted projects with us. The projects have been huge successes. So we'll be talking about what these projects were in the days to come. And again, when you are selected for a QSL fellowship, you also have a chance to work alongside some of the best researchers in the fields and under close mentorship by experts. So it's really an opportunity for you to develop new skill sets, learn from the best in the industry, and get to the next step in your quantum journeys. And this, I think this also brings me to the point of highlighting some of the projects we have had in the past. So you can see some of the success projects we have had. A huge shout out again to NNL, NETL, PQI for hosting some of the projects at their labs, at their quantum conferences. You can see some of the participants who were presenting today in these pictures as well. So you can see how they were invited to different labs, how they got the opportunity to present their work to some of the best researchers in the fields. And all these opportunities are open for everyone here in the audience today. So if you are interested, I would suggest go through all the assignments in the modules, complete everything, do the projects really, really well, so that you are also one of our QSL fellows in the next few months. Again, if there are any questions, please put them on Discord. If you are interested in collaborating with some of the projects presented today, please feel free to mail me or anyone from the Womanium team, or just message on Discord. And if you do have any questions, we are always there to help you out. One final thing before we wrap up today's session are the new partners for 2024. So 3 key partners: Naval Nuclear Lab, Fraunhofer Institute, and Classic. All 3 partners have hosted a quantum project with us. You have the option of selecting either 1 or 2 or even all 3 of the projects to start working on them right now. And the best projects, the best participants will be selected for QSL fellowships. So this is like a direct pathway for you to start exploring different projects, try to find new team members, and at the end of the day, get selected for some really, really cool QSL fellowships.